Hi, my name is Jason, and I'm a solutions architect with AWS in Sydney. And I'm here to talk to you today about GitOps on AWS and with Kubernetes. So, has any of this happened to you? A deployment just failed, and you hear, "It worked on my machine," or "It worked in our staging environment." Or perhaps you have a major incident, and you frantically try to work out, has anything just changed? What changed? Who changed it? And some finger pointing ensues. And maybe that incident means that you need to rebuild some things. So you go looking for the documentation, and if it even exists, maybe it's not up to date. Or maybe things just seem generally out of control. The good news is, if you have any of these problems, then GitOps can help. We'll start with a brief overview of what GitOps is. In order to understand GitOps, we need to take a step back and look at modern software development practices around how they manage change in software teams. Traditionally, there's been three key activities and systems involved in managing that change. The first is the source code management, using things like Git. The second is the building and the testing of these applications, which is normally done with things like Jenkins or AWS Code Build. And finally, we have the deployment of these changes, which might be done with AWS Code Deploy. These systems are often stitched together into pipelines, and there's two major types of pipelines that you see within software organizations. The first is continuous integration, and that monitors a Git repo for changes and triggers builds in response. And then continuous deployment, which is, if those builds and tests are successful, doing deployments automatically off the back of them. And if you combine those two things together, it becomes a CI/CD pipeline that takes you all the way from a committed change to a service that's been updated in production. Also, we traditionally have had a divide between application code and infrastructure. For example, here we see Margaret Hamilton, who led the team that wrote the code that landed humans on the moon in the Apollo program. We also see the Apollo guidance computer, which was a very bespoke piece of equipment. There had been a handover on a team like this, where the code has to be handed over to specialized infrastructure people to deploy and to operate that computer for them. The good news is that this has changed, first with virtualization, and then even more so with the cloud, where we now can have declarative JSON, YAML, or CDK to do this on our behalf. This abstraction has really helped, and it's let us treat infrastructure almost like code. And because we now can treat infrastructure like code, we can manage it in some of the same ways that software developers do and get many of the same benefits. So for example, what GitOps would mean here from an infrastructure perspective is that we have these infrastructure JSON, YAML, or CDK files in a Git repo, and changes to them would either trigger a code pipeline to update a CloudFormation stack, or Flux, which we'll look at in a moment, to trigger those changes on Kubernetes. Flux is a part of the CNCF, or Cloud Native Computing Foundation ecosystem, and it is intended to monitor Git repos and do GitOps around Kubernetes, and it's what we're going to be looking at in our demo. Also, I mentioned the AWS CDK, or Cloud Development Kit. This is a new offering that allows you to represent what you'd like not only in JSON or YAML, but in real programming languages like Python, TypeScript, Java, and .NET. You then, after declaring these things in proper programming languages rather than JSON or YAML, have it compile it into a CloudFormation template for you, and then use that against CloudFormation. However, you would never edit that CloudFormation template directly anymore. You would instead go and update the CDK. One of the benefits of the CDK is that it embeds in it many common best practices, so a few lines of CDK code can generate quite a lot of CloudFormation that represents the best practices that you should be doing within the AWS environment with much less effort. We'll look at this a bit more in our demo in a moment. When we talk about GitOps, a common approach is to have a branch per environment, and you merge your changes to that branch in order to trigger the deployment to that branch. So, as we see here, we might have a situation where each developer gets their own personal branch where they can iterate quickly on any changes that they're working on. And if they're happy with that change, They might then also merge it to an integration environment where they can test it against everybody else's services and changes. And then finally, if things work out well in that integration environment, they might merge it to the production branch to send it to production and have the customers experience the change. In many organizations, though, that might be a little simplistic. You might have, for example, a main shippable trunk that you use to control the change. So you might, as an example, say, after you've had successful integration tests, I would like you to submit a pull request against that trunk, and that's where we predominantly control our change. And then from there, we could deploy to production, as an example. Git branching strategies are a whole talk in and of themselves, and this is an area that you'd have to pay some attention to if you're going to do GitOps well. So that's what GitOps is. Why might you want to do it? First, Git is the tool that all the developers in an organization are already using. So by bringing people like your operations and infrastructure teams along to use the same tool, you get consistencies. You have people that are using the same tool and playing nicely together. Also, it allows management to not only see the changes within each team, but across teams all in the one place. So it can really help with making everybody more streamlined and efficient. It's also a great source of truth because it keeps a full history of our changes, and it serves as a great auditing and reporting tool there as well. It shows us not only who made each change, but what they changed, when they changed it, why they changed it, and who approved the change. On the why they changed it, it's important to make sure that people put appropriate comments in, maybe linking to the ticket that represents the bug or feature request that they were implementing. And when we talk about who approved the change, it's important to have something like an enforced peer review via the pull request mechanism on every change so that you do have that approver and final gate through to production. That also makes it a great place to control change, because if your production environment is your castle, Git can be the drawbridge in the door here. You have a situation where you would force all of the changes through that peer review process in Git. You also would force it through the pipelines that enforce all of the tests that you might want, not just from a functional, but maybe even from a security perspective. And only once that's all happened is that the only way to get things into production. So it's a great way to control things that way. It can also help you with rollbacks, because the only thing you need to do to roll back a change is to pull a prior version and then merge that back in. So as an example, if we wanted to roll back to the last production version, you would just do a git pull of that particular prior commit and then merge and push it back up. It's important to note here, though, that you need to have done certain things right with your database schemas and perhaps API versioning of dependencies to have this work seamlessly, but Git can definitely help you here. Finally, there's an area that bears some discussion around when you manage the cloud directly versus when you manage it via Kubernetes. And this is because Kubernetes has this concept of operators. Operators are a way to extend Kubernetes to do one of two things. You can extend it so that it can manage containerized services on the cluster for you, perhaps a database or a cache or queue, and it'll run that as pods for you on the cluster. You also can use a Kubernetes operator to make requests against the underlying cloud on your behalf. So for example, to manage an AWS RDS database or a load balancer. And so when you look at your options here, they form a bit of a spectrum of options. On the one extreme, you have AWS managed services that you manage directly via AWS with things like CloudFormation and CDK. On the other extreme, you have everything running on the cluster with no AWS managed services. And then in the middle here, we see that you have AWS managed services, but you're managing them from within Kubernetes. The demo that you're about to see is somewhere in between the left and the middle. We have our database, which is our most important piece of managed infrastructure, being handled directly in the cloud via GitOps of CDK, and then everything else is run via operators, things like the load balancer and the secrets. We'll look at that in a moment. So, that all said, let's have a look at a demo. In order to understand the demo, let's go through a little bit about what you're going to see. This demo is an app called Ghost, which is an open source app for publishing personal blog posts. It is a 12-factor app, meaning that all of its state is externalized to its MySQL database, as well as it gets all of its configuration from things like environment variables. It is a well-containerized app by the community, and so it was a great candidate for running this way in Kubernetes and showing off some of these features. What we're about to see as far as how this all interacts between Kubernetes and the cloud is that we have a CDK-managed RDS database. CDK has gone and provisioned a secret in Secrets Manager that has the password for this database as well as all of its connection details. And we need those in our pods in order to be able to connect to the database. So we install an external secrets controller, which is an operator to extend Kubernetes to integrate secrets from Secrets Manager into Kubernetes secrets. So it watches these secrets and it upserts them into Kubernetes for us. We can then reference those Kubernetes secrets from our pod spec and deployment spec. So we deploy our Ghost service, and it retrieves these secrets on the Kubernetes side and is able to connect to the database. To expose this to the internet, we've chosen to use the ALB ingress controller, which is another operator that we can add to our Kubernetes cluster to manage the ALB in AWS. And so we define our ingress object, and then the ingress controller goes and provisions an ALB for us, and it will monitor as the pods come and go and add and remove those targets from the ALB and do other seamless management of that ALB for us from within Kubernetes. And finally, we want it to have a real name, like in this case, ghost.jasonomaker.com, and so we need an external DNS controller to automatically update the CNAME that we want to match the ALB name that is probably not a good experience for our users to be using directly. And when we look at the Git flow that we're about to see, there's basically in one Git repo two folders, AWS App Resources and K8s App Resources. In AWS App Resources, you're going to see a code pipeline invoke a code build, which runs AWS CDK tools to create and manage the RDS database. And on the K8s App Resources folder, we're going to see that Flux monitors that folder for changes, and it updates the underlying EKS cluster and objects to match those changes. The address that you're about to see the demo live in is down below if you want to have a look after the talk. So let's have a look at our demo. We see here Ghost running on the internet at ghost.jasonomaker.com. One of the interesting things about this is that we see that it's an HTTPS encrypted website. So if we look at the certificate, we're going to see that it is issued by Amazon, and it's a wildcard certificate. You'll see in a moment that this is managed by Amazon's ACM certificate management service, and it manages the ALB here as well. So let's have a look at the infrastructure as code that backs this thing. As we said, there's an AWS App Resources folder and a K8s App Resources folder that we're concerned with here. This service has an availability issue. The database is set to single availability zone, and the underlying pod is only running once in one availability zone. And so both of those are bad from an availability perspective, so we want to fix that. What we're going to do is create a new branch so we can make some changes to fix this availability issue. We'll start with the AWS App Resources, and we'll have a look at our Python CDK code that manages the database. What we're going to see here is that multi-AZ, the parameter, is false. We need to set that to true. So we're going to edit this file, and we're going to flip that from false to true. Now we're both going to commit that change and leave a good comment explaining why we're doing it, because these comments, as we're going to see, are important in the peer review process of our pull request. While we're in here, let's have a brief look at the build spec. This is the file that tells code build what to do when the pipeline invokes. As you can see here, we're installing the CDK and running some CDK commands. We'll look at that a bit more in a moment. Now let's go to the K8s App Resources folder and our Ghost deployment spec. We're going to see here that there is only one replica being asked for of the pod, so only one pod will run in response to this, and we want to make that 2 to make it highly available. So we're going to make that change and commit it with our comment here. And while we're in this folder, let's have a look at the ingress object. This ingress object, as you can see, has some ALB ingress specific annotations that say how to configure the load balancer. It also has an annotation for our external DNS controller saying what is the real name that we want to ensure is CNAMEd to the ALB address. Now that we've made the changes that we want in our branch, we want to submit a pull request to get this merged so that it'll get deployed. One of the great things about pull requests is it makes it really easy to see exactly what changed as you're reviewing the pull request. And as we'll see here, it warns us that we're not allowed to approve our own changes. This is because you want a second set of eyes and a bit of control around changes, especially ones that are about to be merged to production. However, for the purposes of this demo, we're going to do it anyway. Now that we've merged our change, as expected, Code Pipeline has noticed that that change has been merged, and it's kicked off a pipeline. So we can see here with this link on Code Pipeline that it takes us right to GitHub and shows us what changes just happened that it's in the process of processing for us. So that's handy. And it also links us directly to code build, where we can tail the logs of what's happening in real time. So as we said, the first bit of this build spec that it's running is it's going to install the CDK. That installation is via npm, and then we're about to see that it also runs a pip command because we're using Python CDK and some of those Python modules are in pip. If I wanted to make this faster and more efficient, I could have included all the CDK tooling in a custom container image and asked code build to run that image instead. However, for the purposes of this demo, we're going to do it at build time. It's now installed CDK and run the CDK deploy command. And as you can see in the output here, it's creating a CloudFormation change set, which it's then going to deploy for us. It's indicated that that update is in progress. And because this is CloudFormation, we should be able to pop over to the CloudFormation part of the console. And sure enough, we see that there's an update in progress on that database stack, as it's changing to a highly available multi-AZ configuration. While we're in here, we might as well also look at the secrets manager and see the secret that the CDK has created for us. This secret includes not just the host name, but also the password of the underlying database, everything that the service would need to connect to it. So now let's have a look and see what is happening on the Kubernetes side of things. We'll start with a kubectl describe on the Ghost deployment, the thing that we changed the deployment spec for to make it 2 instead of 1. And as we can see here, it has scaled up to 2, which is what we expected, which is great. We also can see that there's some environment variables getting passed into the container, and that these environment variables are coming from a Kubernetes secret called Ghost Database. This is the secret on the Kubernetes side that's being managed by the external secrets controller. And we'll have a look at that in a second. Let's also look at the nodes. And this is interesting because the service is running in Fargate mode. And in Fargate mode, every single pod gets a node as well. Because Flux is what has been doing this GitOps magic for us, let's have a look at its logs, and it'll tell us a bit about what just happened. As we can see here, it periodically checks the repo for changes, and it noticed our committed change, generated a Delta Kubernetes spec file, and then applied it. And we can see here exactly when that happened and the timings for how long each step took. It logs that out for us, which is great. Now we're going to look at that external secrets controller to see how it got that secret from the AWS Secrets Manager into that Kubernetes secret that we referenced in our Ghost deployment spec. And as we see here, it looks for changes on that secret, and if the secret changes on the AWS side, it upserts those changes into that Kubernetes secret for us. So that's how that appeared. Finally, let's have a look at the logs of our ALB ingress controller. What we're expecting to see here is that the ingress controller noticed that there is another pod of Ghost, and it added it as a target on that Ghost ALB. And we can see here that that did happen. So it noticed that we now have 2 pods, and it added that. And you can see here in the logs in a prior situation, it also removed a pod from the target group. So one of the key things that the ALB ingress controller does for us is manage the mapping of pods to the load balancer. As we can see here, these are the IP addresses of our pods that are running Ghost. And if we pop over to the ALB console, we'll see those exact same IP addresses as the targets for this ALB. This actually also shows us that they run in 2 separate availability zones, giving us a great high availability story. And if we go to the monitoring, we'll see here that the healthy host count for that load balancer has increased from 1 to 2. You get all of the normal ALB metrics and things because all that's happening is it's managing that for us. So in closing, it's time for you to try GitOps yourself so that your app works in every environment, that your developers and operators use the same tool and play nicely together, that you know the who, what, when, and who approved of every change, that you're in control of your changes, and that you can roll them back to a known good state whenever you need to. Go build.